Okay, so this one's live. I'm just going to bring it in.
Hello. Hey guys, if you don't mind taking a seat, we'll just get started up. There are a number of chairs free up front here. You can come up here and sit down. So, alright guys, thanks for coming again to the Big Data User Group. Tonight we have a great talk about, Cassandra, CQL, Storm, and to create an iPhone app. Before we do that and get into the talk, I just want a quick question. How many of you attended Big Data Camp a couple of 3 weeks ago? So what do you guys think about it? Good? Good? Yeah. Yeah, we had a pretty big turnout for the event, close to about 600 people. That was pretty awesome. We're probably going to do this once a year, so next time will still be next year, but we'll try to see if we can get a bigger space, if we get more people attend. Alright, I would like to invite Becky from Cross Campus to just do a quick talk about Cross Campus and what we do out here.
Hi guys, I'm Becky. I'm the events director here at Cross Campus. Thank you all for coming tonight, and thank you, Subash, for organizing this group. You do a great job. Events is a huge part of what we do here at Cross Campus. We like to bring members of the community into our community, and what we are during the day is a co-working space. So we have our own community, and we like to connect with all of you. And if you're interested in what we do during the day, when we're not hosting events and meetups and concerts and World Cup parties and all the other fun things we do, you can talk to me, you can talk to any of the members of our team, you can get some information at the front, and we would welcome you in for a day pass to check out our space. We have a lot of cool, creative technology, startup, everything going on here. We're kind of the center of all of this in Santa Monica, so please come by, ask us some questions, chat with us, and we're happy to have you all here tonight.
Thanks, Becky. Now I would like to invite Scott from DataStacks and Cassandra. They are sponsors for today, so he's going to give a quick talk about what they do.
Thanks. How's it going, guys? I'm using my little cheat sheet here. And we're going to do a poll. How many here are first time, just interested in Cassandra, just kicking tires and doing some education? Wow, okay, that's awesome. And how many are using it today in development environments? 3, 4, 5. And what about production? 1. Awesome. It's coming. It's coming. Okay. Anybody going to the Cassandra Summit in San Francisco in September? So it is happening in September. It's going to be massive. It's on our website in case you're curious. And I'm just pumped, for this happening tonight. I think we're in this revolution of, relational to non-relational. You could be sitting next to the next big hot data guru of the future. So it's cool to see you guys. And so the community itself, there's now over 3,000 either companies or projects using Cassandra. When it comes to DataStacks, the corporate entity behind the movement, we now claim 500 enterprise customers. And actually makes up 25% of the Fortune 100. That's pretty amazing considering we've been around for 3.5 years. And our CEO, in fact, today was in a press release saying that his goal, and he thinks it's realistic, that we'll have 100% of the Fortune 100 in less than 10 years of being in existence, and that's just disruptive. A couple local customers I want to call out because you might know them. Using Cassandra, Callfire, JD Power, Reach Local, Newegg, Hulu, Sony, Activision, Intuit, and a lot of early stage startups, Shift as a company. Just 2 weeks ago, we had a big announcement of our new release, and I'll call out 2 interesting things about it. A newly announced integration with Spark. Everything's kind of going with Spark now. You'll hear a lot about that. So for sort of real-time analytics, and also integration with Hadoop, we're now partnered and certified with Corp and Cloudera. So those workloads that need to run both real-time operational versus historical data, you can blend that together now. And if you want to learn more about some of these announcements, we're having a webinar tomorrow, DataStax is, that's going to talk about that whole announcement and everything going on around Cassandra as an enterprise product. And to give you just a heads up of who your resources are here from the community and from DataStax, I'm 60 days new in the company. I support selected enterprise accounts in SoCal. We have headcount to hire a strategic representative for some of your biggest brands like the Disneys and the Boeings in the region. We are looking for a pre-sales solution architect. Send them to me. We need help in that area right away. We recently brought on a new technical evangelist right out of SoCal, right out of Hermosa Beach, John, back there. So attack that guy for anything. He's the guru, no doubt. And thanks for having us.
Thanks, Scott, and thanks to DataStax for sponsoring today's event. I would like now to invite Dan, who's going to be a presenter for today. He's going to be talking about the iPhone app Tappy that they're working on, and some of the great tools such as Cassandra, CQL, and Storm, and how they're using it. Please give a warm round of welcome to Dan.
Thank you. Really appreciate it. That's very cool. I have to laugh at that. Okay, oh, thank you. Okay, so I didn't even realize the DataStax folks would be here, but Scott was nice enough to ask about how many of you were using Cassandra, and it actually seemed like it was pretty low in numbers. So what I'll do is, as I'll dive in, I'll start out with some stuff that's pretty basic, but I'm totally happy to vary this up and just kind of nod or like faster, or slow, or feel free to interrupt with questions and discuss stuff. I'll say I do a little of everything, so I'm not a huge expert, but since some of the DataStax folks are here, worst case, we can defer to them on some things. That said, my impression is also that the Big Data Group has, folks here are very sophisticated comparatively about different tools, big data stuff, so I'll assume some knowledge of all of this class of data stores and other systems, but please stop me at any time. So what I want to do is give you a little history of what I'm working on, how I got here, what it is, and then dive in a little to some examples. And I want this to be a really practical thing. I want to look at, hey, I want to look at how do we use Cassandra from a programmer's point of view. And it just so happens that I'm going to use an example of an app that we're currently working on and actually just about to launch. So the only real Tappy reference you'll see, you'll learn obviously a few small details of the app, but the only real reference you get is this logo up here. Though if anyone's interested, grab me a little bit later. And I want to talk about some of the architectural choices, how we decided to do it. Now, the one warning I'll give you is that this hasn't been proven at all in the real world, right? So everything I say here comes from a lot of experience in building systems that operate at scale. However, this particular system that we're going to run through the architecture of is based on all the lessons we've learned to date, but if the lessons are all wrong, that was your fair warning. So to tell you a little bit about myself first, before we dive into the more technical stuff. So I'm more of a social product designer than a back-end engineer. So I always look for, how do we find the shortcuts? How do we do this effectively? Some of the more, back-end engineers of data will care far more about the implementation details of gossip protocols and hinted handoff and all that. And if you want to get into it, I took a lot of distributed systems courses in school, so I can pretend. Now, I worked, some of these scrolled off a bit, but I've worked on a few systems over time that have operated at scale. So my first company was one of the early, way pre-MySpace, pre-Friendster social networks, and that had huge, huge scaling problems. So that was the one I get to leave off the slide because I messed it up so badly. Then, a few years ago, I worked on a tool called Newroo. So we were up in San Francisco, and Newroo was doing machine learning-based news aggregation. So we were in real time spidering a lot of real-time news sources on the web. So blogs, newspapers, all sorts of other sources. And this was in the pre-Twitter days. And trying to personalize things based on your interests. So a lot of that was, how do you scale the real-time spidering? How do you do machine learning fast? And how do you keep up in a very real-time sense? And a lot of that was building real-time in-memory databases. And nowadays, that whole class of things exists in various forms, in the form of Memcache and Redis and some other fancier stuff. Over the years, there have been lots of things in that world, tuple spaces, and so on. The way I ended up in Southern California was we sold Newroo to News Corp. So then I was, for a few years, VP of Technology at Fox, and we owned MySpace and a few other properties. And a lot of people in the LA scene worked on that. I was not behind a lot of the architecture there, but there were a lot of really interesting architectural aspects, right? In that day, everyone used SQL databases. And then the answer was, how do we hack things to scale? So they started to hit they were using MS SQL. So they were using Microsoft SQL. They'd hit a scaling limit, they'd shard it, and then they'd hit another scaling limit, and they'd build whole database clusters that were for one join table. So this was kind of the learn as you go, hack it version of scaling. But there were a ton of interesting lessons there, right? Now, one of the big picture lessons of that whole era, I think, was how NoSQL was born, right? So first, by a quick show of hands, how many of you in whatever production you're using are using a SQL-based system? So call it 3/4. And how many of you are using some sort of NoSQL-based system? Okay, so about the other quarter. I'm sure a lot of people have both in various states of production. And SQL is actually one of the, you remember the old bumper stickers, COD is God? God related the relational calculus, right? Relational databases are amazing. They do some really cool things. But what happened is, as we started to build internet scale systems, you run into lots of problems with the SQL model, right? With the relational model, just of practically implementing it on internet scale systems in terms of availability, in terms of scale, in terms of a lot of particular details. And what happens is everyone starts to hack together these solutions. They start to hack together these we'll shard this, or we'll denormalize the table here, right? And anyone who's using SQL, how many of you who are using SQL have hacks like that in their data today? So I'm seeing at least a few hands. You're starting to hit scaling problems. So once you do that, you say, well, I lost all these great, cool benefits of SQL, right? The ability to do arbitrary joins in various ways. What am I getting in return? And so a few years ago, a lot of the big data community started to hit that of, hey, let's break some of these assumptions. Let's give up ACID. Let's give up certain aspects of relationality. But then once you decide to do that, instead of just sharding your SQL database, you say, what can I get in return, right? What do I get for breaking some of these assumptions? And it turns out you can do a lot of really cool things. So we'll end up touching a little bit of those. Then there was, within Fox, we did Fox Audience Network, which at the time we grew to be about the 4th or 5th largest ad network in the world. So that was actually a really interesting, different set of challenges. And what we were doing was build a small online model for deciding what ads to serve. But then because we had the whole traffic of MySpace and huge numbers of the internet, we were doing about 6 trillion impressions a year. So every one of those impressions had to be logged, analyzed, used to rebuild the models. So once you start to operate at those scales, you start to do really interesting things. So we were very, at the time, this was years ago, early adopters of Hadoop for a lot of our model building, and a lot of the business analytics folks use Greenplum, which is a Postgres solution that is an interesting distributed Postgres. So that's kind of my personal history and where I come from. Then we have a company that we've done a few things within, and I'll just mention a notable project, which is Chill. And Chill's gone through a few iterations, but one of the key things was we had a video discovery service. And we started out the video discovery service and quickly figured out, so we built it on Postgres. We said, this is easy, this is fun, we know it, we can build there. And we figured out the right viral loop. And very quickly, we ran it up in the course of about 2 months from 0 to 30 million active users. Now, we weren't prepared for this technically at all. So a lot of what we were doing was what some of you have been in that situation of. We've got servers, they're not scaling, we'll hack a solution, we'll throw in a caching layer here, we'll throw in a caching layer there, and we'll figure out how to throw a big array of disks at this Postgres server, we'll shard this. Things are constantly breaking, and you're constantly racing to keep up. It's a lot of all-nighters and a lot of pain, and anyone who's more on the ops side or who's been engineering this, I'm sure a lot of you here feel my pain. So what we started to do was we finally got enough headroom that we were able to go back and say, how should we do this right? And we started to play with some NoSQL data stores and did a little bit with Cassandra, but just started at that point. Due to a whole bunch of complex business reasons that would be better to talk about over beers than, let's see if I can get this on, that would be better to talk over beers than in a lecture, we ended up winding that down. But I said, next time we do it, we're going to do it a little more right and have a chance to think it through in advance. So really what I want to talk about and look at are some lessons of that. Some very, very high-level lessons first, right? Everyone who's been in computer science for a while knows the famous Donald Knuth quote, premature optimization is the root of all evil. And you're looking at me like, okay, you're about to tell me about using NoSQL instead of SQL from day one. Do you actually believe what you're saying? And I think that there's premature optimization, which is tuning things just for the sake of tuning them, just for the sake of being fast. But then there are good architectural decisions. And in some cases, certainly not all cases, but in some cases, starting from the point of view of scale from day one can be a great and important decision. And this is how we try to get stuff right for what we're building from day one. So just to give you the quick example, we're building a new social app here. And the social app we're going to look at, I'm going to elide most of the details. But you can guess a few things, right? A feed of images. So you have to deal with how do you represent a data feed? And we'll come back to this in a few, which is a time-sorted thing per user. And then you have lots of other things that are more like key value in a way, right? You've got, this is looking at one item, and it happens to have some chat stuff come in. So you've got profiles, you've got user data, like this is, my friend Brian is listed here. So you have to load certain data one-off. And once you're dealing with a lot of stuff in the NoSQL world, you start to think a little bit about how are you going to access it, what are the queries you're going to do. So I just wanted you to have in your head that, okay, we're talking about an app, it has some time-ordered elements that are per user, and then some things that are very much about particular user lookups that are kind of one-offs for a data item. That make general sense? Getting some nods. Okay, so that's way of background. Then I want to talk a bit about how we chose tools for our particular platform. We looked at a whole bunch of different types of tools. And I think one of the cool things in the world is that there are so many tools people have come up with and built in the open source community that solve different classes of problems. And I'm a big believer in right tool for the right job. For what we were doing, we looked at, first thing, hosted data stores. So using Amazon DynamoDB, SimpleDB, there were some other providers. We happen to know AWS pretty well, so we at first looked at the AWS things. We know Postgres very well. That we spent a lot of time deep in it and learning to tune it and tune kernel buffer, everything you could do to eke a bit of performance out of Postgres. So we looked at that very seriously. We looked at document stores. So I'm not going to go into it, but there are document stores that typically represent something as JSON or XML, at least externally, but they have a document and a data structure, MongoDB, that sort of thing. There are distributed key value stores like Riak and all sorts of others. And then I'm putting Cassandra, now that I'm standing here, I was thinking I should maybe put it as its own category of column stores. So things that represent something that looks like a table, right? Something you're kind of familiar with, but thinks about it in a very different way. It's not necessarily rewriting whole rows at a time, it's dealing with columns. So HBase being maybe the most pure classic example of that, and Cassandra being an interesting case. Then because of some of our goals with this, we didn't consider a whole bunch of other classes of things. Now, I'm a developer. There are a lot of ops people, and ops people think of the world in one way, developers think of the world in another, and usually the things that developers love, ops people hate, and so on. Thankfully, we're trying to get our product launched, so one of my good friends, who's also our head of ops, is sitting in the office trying to make stuff work, so he can't be here to throw tomatoes at me. Now, from the developer perspective, we said our goals were, we wanted to have something where the data model was very easy to represent a feed, right? Something the internals would say, hey, I want to load a feed, boom, I want to load it fast. I want things that are easy to write code for, good Python support, and easy to evolve a schema. One of the cool things, for those of you who are in the SQL world, about a lot of these NoSQL data stores, not an implicit fact about NoSQL, but almost all of them tend to have very flexible schemas, where adding a column or having sparsity, where you have a whole bunch of columns that are null or something that's tagged on a particular item, turns out to be really easy. It's kind of like the difference between statically typed languages and dynamically typed languages, for those of you who have done a lot of each. So it turns out to be one of those things that doesn't sound like a big deal and isn't like a good punch list feature, but as a day-to-day developer, it means a lot. The ops people obviously have their set of requirements. I hope I haven't been blocking this the whole time. High availability, scalable, multi-data center, which turns out to be a huge pain in a lot of different worlds. And ideally, no special nodes, single points of failure, master nodes, that whole side of it. So as you might have guessed, especially given the title of the talk, our decision was to go with Cassandra. So we said we'll be NoSQL from day one. Now, this is something that I'm not saying, hey, just go do it. For a lot of apps, particularly the sort of small one-off apps that you write, and up to a pretty decent scale, I actually love SQL, right? It lets you very quickly say, oh, I thought of the data in this way. No, I'm going to change the index to that. Oh, I'm going to join in this way. You don't have to think about a lot of things in advance. So that's a great thing about SQL, that as you're evolving things, you can change it around a lot faster in certain ways, though the tools now around something like Cassandra are evolving to make it almost as fast, but they're not, in my opinion, at quite the same level yet. So it's an interesting discussion to have when you're starting to think about an app. So why did we do this? Well, I gotta say arrogance, right? I think that we're building something that will operate at the scale that will necessitate using a NoSQL data store where it'll be easier for our lives, where we'll be dealing with all that, and this makes that classic problem just disappear. Okay, so this is, for the app that we're building, I'm going to give you a very high level of the architecture we're looking at, but then we'll go into a little of what it actually does. So as I mentioned, it's an app on the phone. The phone is then connecting to our side of the internet. And it's living on Amazon. So in AWS, they call their load balancing service ELB. And there are actually more than one of these, but the diagram would get too complicated too fast. Sitting behind it, we have a bunch of caching servers that manage the web servers. So Varnish sits there. In our case, actually, because you don't tend to, in a phone app, you don't have the same thing. How many of you are doing phone apps first thing? How many? Okay, decent number. How many of you are involved in web apps? A pretty good number. And how many things that are totally different? Back-end systems that have nothing to do with either the web or phone. So call it 10, 20% doing phone stuff, then split pretty evenly between web developers and kind of everything else in the crew. So one nice thing on the phone is that the phone is doing rendering, it has code, you don't have to send over a whole bunch of stuff. The bad thing is it means almost nothing is cacheable, right? We tend to be sending API requests that are unique per user, so these just deal with some nice things about HTTP termination and SSL, but the Varnish servers don't do what a Varnish server does on most websites. We don't use it for nearly as much. Then we've got the web server sitting here. We're Python developers, so we happen to if some people put an Nginx in between, we don't. Kind of doesn't bias anything. So we tend to use UWSGI. If you care about technical details, we're using Flask as a framework. But really, the whole idea is our web servers are queuing events in a queue, and more importantly, they're doing almost all their operations against Cassandra. And what we said was, this simplifies our architecture, right? So we used to do things that had architectures that were talk to Postgres, talk to Redis, talk to queuing service. You talk to about 30 different services. And we wanted our whole universe to be automatically cross-data center. So we said we want to set up a set of services, and only a few services are allowed to even know that other data centers exist. Otherwise, your web server talks to some small set of services in its own data center, and those other services should handle everything behind the scenes. So we said our fundamental cross-data center service, there are a few other slight cross-data center things, but our fundamental cross-data center services are Cassandra and Zookeeper. And Zookeeper really, outside of a few other cases I'll mention, is just managing settings and configuration and a few things like that. We tried to keep Zookeeper, for those, how many of you have used Zookeeper or are familiar with it? So call it a third. Zookeeper is a distributed coordination server. You can use it for locking, you can use it for certain sorts of counters, things where you care about deep sort of cross-data center, cross-process communication. We can do a whole talk on it. Ask me questions later if any of you care about it, but we'll ignore it for a second. Cassandra is our fundamental cross-data center thing. So we say you write data, you read data, and all of the how it syncs between data centers and other stuff lives there. And then we use Kafka for queuing, and on the other side of this, I didn't quite have space on the chart here, there's some Storm stuff which we'll also touch on briefly at the end. Okay, so given just the data stuff and what I was hearing, I originally set this up to be kind of Cassandra, Kafka, and Storm. This talk, feel free to ask questions later, but I've kind of set it up as 80% Cassandra, 20% everything else. So Cassandra, I see as kind of like the Reese's Peanut Butter Cup tool. And that's the reason it's interesting. So to look historically for a second, there are two papers that I thought were really, really cool when they came out. And I think a lot of people, if you read Hacker News, some of these might have been pre-Hacker News, but if you read that sort of stuff, it was like, wow, I'm going to stop and read this. So I think it must have been Jeff Dean, but some folks at Google published a paper a few years ago called Bigtable. And they said, we're dealing with these giant data stores. How do we organize data in a way that's effective for it? And they came up with this idea of the column-oriented database. And I'm not going to go too deeply into it, though, as I said, feel free to do it. But basically the idea is you have a data store where each column is treated separately. So you can write them independently without writing over an entire row. Means a lot less locking. And then it looks at timestamps, more or less, to resolve which version of stuff. So you can have lots of independent processes writing things to columns in these column stores. And then you can resolve the most recent version of data. It is actually makes things very flexible if you don't care about exact locking semantics. If you don't care nearly as much about transactionality, you can do a whole lot of things a lot faster. And it also opens things up so it's easier to add other fields. So this lets us have the flexible schemas we were talking about earlier. The other cool paper that I read back in the day, and I suspect a lot of you read, was about Amazon Dynamo. So there's a whole bunch of research, like Rice and I forget where else, on distributed hash tables. They were saying, how do we use consistent hashing? How do we keep a ring of data and make it easy to have something that's highly available? So we know that, we're going to replicate the data. So let's say we have 10 nodes in a ring, right? If we know that data with key 5 always ends up on nodes 1 and 4, we can figure out, that should be on nodes 1 and 4. If a node dies, we know exactly where to replicate it to, where to move it to, keep it consistent. So now you have a highly available system, right? Some nodes can fail, and you still know where to find things. And it knows when a particular node fails, how to re-replicate data across the ring so that you always have a certain number of copies. So you say, okay, if I'm going to build a ring and say, I'm going to have a replication factor of 3, I know at any point in time the system is going to try and maintain 3 living copies of my data. That's actually a really powerful thing. It means that you can have online access and a highly available system. So something I never thought about, but that some folks at Facebook thought about, was why don't we put these two ideas together? They actually feel like completely different. Bigtable feels like heavyweight data storage. Dynamo felt like, hey, this is how do we do key value stores really effectively and fast. But they fused it into one thing. Now the weird thing is, it was written by a bunch of folks at Facebook. And when Cassandra was in its early days, it took a while to evolve as like a really awesome open source project. And Facebook just needed to scale at that moment. So they actually hired up a ton of the HBase developers. So they used a lot more HBase internally, whereas a lot of other people got the benefits of their work who came a few years later and got to use the, in my opinion, much more modern Cassandra. But an interesting historical artifact is the place that invented it is maybe the one place that doesn't use it, or at least use it heavily. So fundamentally, we said, it's decentralized, multi-data center, scalable, and the interesting bit we'll talk about is tunable consistency. So I'm actually going to skip over that because I think we're doing more time. We talked a little bit about rings. So fundamentally, you set, in configuring your nodes, you're setting up, hey, I've got this ring of Cassandra things. I'm going to set up how it replicates data. So I can say, I want to ensure that there exists this many copies in this many data centers. Here's how many nodes are in the ring. And then the thing that the developer, or the thing that the end user is going to care about is the consistency level. So they're going to say, if I'm going to do a read, do I just need to find one copy of it? Do I need to find a quorum? So in this case, of my really simple, let's say we have a replication factor of 3 in this really simple ring. So we said all data exists, 1, 2, 3 places. When I do a read, do I need to find a majority, right? Do I need to say, okay, we've got 2 copies of the data to say that I've got it, and I'm doing a valid read. So that's kind of a quick hand-wave explanation. Does that generally make sense to folks? Okay, I'm getting some nods, but feel free to jump in. So that says, on any write, we can say, okay, I'm going to send the Cassandra cluster a write. And I might send it with a consistency level of 1. What that says is, it needs to get to one of the nodes that's eventually going to hold it. Now, once it reaches that consistency level, it's going to return from my function call. It's going to say, you wrote it, you've been successful because you had a consistency level of 1. That doesn't mean it's only going to make 1 copy, right? It's still going to replicate it to the replication factor you set behind the scenes, but your risk there is somehow this node, you write it to 1, then the node burns up in a fire, right? and somehow before it replicates to the cluster. So some data is more important. You might say, I want it to reach a quorum. So in the case of my replication factor of 3 that I said, it's going to wait till it's on 2 nodes before it returns to you. Or I could say all. So I can tell it exactly how much I care that this data is consistent and that it's just safe, that it's written. So I've been using the example of safe because because consistency is similar but a bit trickier. So that's what they mean by tunable consistency. I get to control on a per read or per write basis exactly how my data is replicated before it returns. The underlying system will always try to get to the same replication level. This thing, on a query, what am I waiting for? And you can actually do lots of very interesting use cases. If you really care about your data, you can force it to get to all of them. Sometimes, now if nodes are down, that'll cause all sorts of problems. Often, you'll say, I care a lot about it, so I'm going to use a quorum when I'm writing and a quorum when I'm reading. And that lets you get to a consistent state very quickly. So just to give you a sense of some of the levels you have within Cassandra, there's any, which just says, get it to any node. I'll connect to some random node in the cluster. I'm going to write it. It may not be the node that actually is going to write it to disk. It's just get it into the cluster, and I'm done. That's super fast. You can write an any at incredible rates, and it will buffer it and eventually get it to disk. But it's higher risk. You can do one, which says get it to one of the nodes that actually owns it and get it on disk, right? There's a level called 2 that I found in the code, but it's not documented, so I don't know if the Cassandra folks want us to use it or not. There's local quorum and each quorum, which have to do with multi-data center stuff. That's a little beyond the level we have time to talk about. There's all. The one thing that I'll tell you is when I started to write this, I understood the theory of it. So I was like, oh, you should read at a quorum and write at a quorum. And then you'll have all sorts of nice consistency. But it turns out that if you just do one, it's so smart about finding stuff because of some of the stuff we're not going to get into, instant handoff and read repair and all sorts of magic stuff behind the scenes that it's doing, that if you read and write at one, for huge classes of data, it actually works shockingly well. You just write, you read, you tend to get what you want, especially in use cases like ours that tend to be very insert only. We don't update a lot of data, we just do a lot of inserts. And if you're doing a ton of inserts, due to some stuff that feel free to ask about later, we could get into, but basically, if you're just mostly doing inserts, just writing at one and reading at one usually works shockingly well. So that's my one empirical lesson we learned. So I wanted to dig in a little bit about how you as a developer might actually use this. So we talked a little bit about how Cassandra works, how you can think about the ring and the app. Now, a few years ago, Cassandra had this whole thrift protocol that was weird and complicated and generally confused the hell out of everyone. That was the point of view. And I spent a bunch of time figuring it out, learning it, and I was like, oh, now I get it, this is cool. And when they introduced CQL, I thought, this is kind of silly, right, to make it look like SQL. But it turns out that it makes things just so much easier to understand because so many people know SQL so well that you can get up to speed and start doing useful things in Cassandra in a few seconds. So there are lots of things you can do in SQL that you can't do in CQL, and a few cool things you can do in CQL that you can't do in SQL, but it's surprising how much they're the same. Now the one thing, since there are some DataStax people in the room, I am going to give them a hard time about, is that on the Cassandra mailing list a few years ago when they said, this guy Eric who came up with CQL said, oh, I have this new language, we're trying to figure out what to call it. I said, it should be called prophecy. Shouldn't Cassandra speak in prophecy? So, no one listened. So, that's, I guess, how it ended up with this awful name, but great tool. So, I'm just going to show you a bunch of examples here and we'll talk about it. So, the most simple thing is you create column family user, and I set up a really simple column family. Column family is the Cassandra name for table. They actually use table as an alias, so if you type create table, it'll still work, but I don't like being sort of real Cassandra. And you'll notice that it looks a lot like SQL. Okay, I created some row, it happens to be called key, they like that in their world. it's, a varchar, and I set it to be the primary key. I put in, just so you see, another data type, so they have text types and integer types, and most of the sort of things you'd expect from SQL. Now, one thing that you'll notice in here that's really important, though, is that you have to have a primary key, right? In SQL, you don't, right? You can throw in arbitrary rows. In Cassandra, primary keys turn out to be super, super important about how they think about the world, right? We just said that they store things in different nodes. Well, how do you know what node something is stored on and where on the node it is? It's, in a lot of ways, a hash table, right? The top level of it, we're going to dive in a little bit and see that it's more than that. But the first way you should think about Cassandra before you build a more sophisticated data model is, oh, it's kind of a fancy hash table, okay? So where the hash table is, the top level looks like your key, and all the values are at the result. Now, obviously, since this is a more sophisticated data store, your next piece of your mental model should grow to say, oh, it's not key to value, it's, I have the equivalent of what we'll call from a SQL world a row here, right? It's not really a row in certain ways, but we'll say, I've got a row here. Then, let's see. Then you can see I can run most of the same sorts of commands, right? So insert into user. I said my key is a UUID here. Cassandra actually has UUID type, so I shouldn't have made this a varchar. That's actually, if I'm doing it better, we should make that a UUID. Cassandra knows about UUIDs and loves UUIDs. Use UUIDs all over the place. And, oh, let me actually stop for a second and say, why UUIDs? Right? A lot of you, I haven't used SQL in a few years, but my memory is kind of, a lot of people do the primary key, integer sequence, whatever, right? This is a distributed system. You don't get to do integer sequences like that, right? Because on any kind of large-scale distributed system, doing counting in very clean sequential stuff is a topic that's incredibly complex, and there are a lot of PhD theses written about it. So it's easier just to say, do stuff that doesn't require centralized coordination. UUIDs are really easy to not have centralized coordination for. So we inserted a key, a username, and then my name, and some my password, right? Now, so that looks just like SQL. Next thing, we can do the same sort of thing with updates, right? Update user, set first name equals Daniel. One thing I could have done with either of these statements that I actually just realized I should have shown you, but I'll tell you about, is I could have done with consistency level equals 1 or whatever I wanted. So I could have added, there are a few different things I can add that tell Cassandra to do specific things. But fundamentally, you can think of those as adding stuff on. Now, likewise, I can do a select username, first name, select some data, where the key is equal to this, right? So I can read back, and it'll give me back the data. And I can do that with the consistency level if I want. But notice this crossed out one at the bottom. I could query it by key, but this version on a SQL database, if I had queried by username, it would have, if I didn't have it indexed, it would have done a full table scan, right? I'm remembering some SQL. You should all be impressed that I remember something. But here, it's not indexed by it. There's no way to tell Cassandra, go and scan all the usernames. There's no index. It's not the primary key. I can't look up by it, okay? So, you do get some cool things here, and we'll talk about primary keys in a second. You do actually, if you want to count things, you get distributed counters. So I can keep adding to stuff and add values. So I can do lots of things I don't get in SQL. I can count in a distributed system in an incredibly fast way. I just don't get exact sequence. It may take a little while to resolve. Likewise, I get all sorts of fancy data types. So I could have included in my table, and I know some fancy SQL engines have it, but we're talking compared to standard SQL. I get sets, lists, maps. So I get all sorts of interesting data types. So I could have a set of other strings or a set of flags. So there are some cool things you can do, but I'm going to skip over most of that for now. The key to understanding this, as I said, is thinking about your primary keys. So there are actually two types of primary keys in a Cassandra universe, or in a CQL universe. There are partition keys, which we were just talking about. You always have to have a partition key, which is where am I in this key value, right? How could I ever insert into a hash table or a dictionary if I don't have a key, right? There's sort of a key value element. Now, sometimes you want it to be based on more than one thing. So you're allowed to have a compound primary key. You could say these three fields are in essence concatenated together to make a primary key. The other thing you get are, after you have your partition key, you can have clustering keys. You can say order by other things, right? So what I can do is say order by time, or order by index, or UUID. I can say, my first key says basically, go to this place, go to this node in the ring, find this location in memory or disk. Once I hit it, I then have a list of items, and I can pull out a range of items. So I can say where something is between this and this, or where something is equal to it, or the newest 5 items. So basically think of it as, first I have a dictionary, then my next set of keys are kind of like a priority queue, or to just simplify it, a list, an ordered list of items sitting after it. And that's what clustering keys give me. And you can have multiple ones, just like you can sort by multiple things. So if I query, I can do a range. I always have to specify primary key, my partition key. Then I can specify I can use my partition keys in order. So I can't, if I have a partition key A and clustering keys B and C, I can say find something where partition key equals A and the next key is less than 5. But I couldn't do where key C is less than 5 because I have to go in order, A, B, C there. So when doing this sort of stuff, UUIDs are great. And it turns out that, I don't know if UUID, because I'm so in the Python world, there are a few types of UUIDs. There are UUID1s and UUID4s in Python. Do UUIDs and UUID4s make sense to everyone here, or is that a very Pythonic thing? Okay, so some people I'm getting a sense that some people. So UUIDs, there are a lot of different ways to generate them, but some are random UUIDs, right? So I'm going to take 16 bytes of completely random data. But then there are time UUIDs where certain bytes in there represent the clock. And Cassandra is actually aware of time UUIDs. You can say, I want my clustering key to be a time UUID. So it's aware of the time fields, and it extracts those subfields and uses that to time order things. So if you have time ordered data, there are really cool things you can do in Cassandra. So then, to just mention some other stuff. Cassandra has this thing, secondary indexes. You see them, you're in the docs, you're like, oh cool, I can do everything that's in SQL. That's actually a really bad idea in my opinion. They're there because I think people ask for them. But they make all sorts of guarantees about consistency between them. If you update one, it keeps the others in sync. The NoSQL ethos, in my view, is you think about how you're going to access the data. You think about your queries, and then you structure your tables, denormalized, so that you match the end result. And so I'm going to look up a feed, and as you saw in that example, I'm going to look up a feed, and it's who's going to access it, right? One of my users is going to access it, and they're going to want a time-ordered feed. So clearly, I'm going to access it first by user ID, then by time. So my data should not be organized by, in SQL world, you'd use third normal form, right? You're like, this is the abstractly perfect way to represent data. The NoSQL world's far more like working, it's roll up your sleeves, which is, how are you going to access the data? And I'm saying my users are going to access it by user ID, then by time. So I'm going to store it by user ID, then time. And if I want to access it a different way, I should write it a different way. Now, Cassandra secondary indexes work, but they're very expensive. It turns out writes in Cassandra are so crazy fast that, in my opinion, if you're going to access it 3 ways, you should just write it the 3 ways yourself and never touch the secondary indexes. Maybe someone will tell me different, but that's just my experience, that you can get crazy, crazy, crazy performance out of it if you're willing to do a tiny, tiny bit of work yourself. And so in our Python level, we've wrapped it so that we can just say, if we want to write it 3 different ways, we'll just our higher level library that we use to wrap it. We'll just say, we want to write it these 3 different ways, and then it'll manage it behind the scenes, which is kind of fun, and I'll talk about some of that in a second. So basically, build your own query tables. Don't let it do too much. And it turns out the DataStax folks are here. I just figured I'd mention. We started out with open source Apache Cassandra. We're actually a customer of theirs, and 99% of the reason I signed up was because we want someone to call. You know, if you're using any kind of serious data store to underlie your company, I want someone there. It turns out it just works, so we don't call them, but I like having a number of someone I can call in an emergency, so that's fundamentally why we signed up. But they do a whole bunch of cool stuff. The main one the reason I even created this slide was because I thought this was such a cool feature. They have analytics clusters, which is, how many of you have had to deal with ETL stuff? Okay, of those, we keep your hands up if it's incredibly painful. Everyone who's dealt with ETL, it's incredibly painful, you hate it, right? You have all these fact things in the database, you're like, okay, now I need to load it into some other database for analytics, whatever sort of roll-ups I'm gonna do. They had this really cool idea, which is Cassandra supports multiple data centers. They said create an analytics cluster, which is a virtual data center. So you set it up, you can put it in the same data center as one of your others. You create a separate data center, and that data center is read-only. So all the data replicates into it, but you don't use it for your live traffic. So now you have this whole offline data center that doesn't care about performance that you can run big Hadoop jobs against, but it's all in real time. So you never have to do any of the ETL stuff. So I haven't actually used this yet, but I was so cool that I was like, oh, we signed up with DSE, and I want that feature. So now I'm going to move on a little bit to how we use it and some of the practical levels, but I'm just going to stop for a second and say, does anyone have any questions? Because I kind of tore through some Cassandra basics. Cool. So what we do is we use we're in Python, we use something called CQL engine, which is an object mapper. So it's a lot like an ORM, except you can't call it an ORM because this isn't a relational world. But I'll give you an example from our actual code. I just pulled out a few fields from some of the databases. So, this is in Python. This is our user model, or a tiny, tiny piece of it. So in this it's a declarative language, or a declarative, what do you call it, domain-specific language, I guess, within Python for declaring CQL models. So this turns it into all the statements. So you see our Python model, we set up an ID, which you'll notice is a UUID, and as I said, it's a UUID4, which in Python is a random UUID. We have some other data about users. I actually just kept this one in just to show you that it has cool, fancy data types that we can wrap, and from a Python user's perspective, it looks just like any other set. Then we have pretty standard fields and where you'd store columns. So this looks like anything else, and pretty much we access it by, I want to look up a user, give me the user ID. It wouldn't even make sense to think about ranges of users or looking up users by their hashed passwords. So users are something simple to look up. So that's kind of the simplest case here. Does that all make sense? So I'm glad that one's pretty clear. So let's go on to something a little more real, which is a post. Okay? Now you say, the post, the ID here happens to be a time UUID. And you notice the default there is a UUID1. So that's in Python a time-based UUID. Even though right now, on this particular table, I'm using it as the partition key. So I'm saying, hey, let's store it by that ID. Even though it's a time UUID, it's going to be randomly distributed through the node. Then we have a bunch of other data here about, who did we send it to, what's the data. I just pulled kind of the first few lines of code, so I don't even know which ones fit on the slide. And some of these are our own wrappers, so we just wrap, at the Python level. There's no real enum type, but we just happen to wrap it. Okay, so this is where it gets interesting. This is the almost exact same data, okay? As was in the post, we denormalized it onto a second query table, okay? Now the second query table is a user's inbox or their feed as you see it. So you'll notice, and they told me there's a laser pointer on this. Let's see if I can do that. Yeah, so you notice now we have that same post ID that was up top in the post, but notice before it, we have our partition key equals true, right? So I said, first, we're going to start with the user ID. That's my first thing. Then the second thing is, Cassandra, as I said, is aware of time user IDs. So it extracts the time of these, and notice it's sorted by descending time. So now if I have a user, they log in and they say, give me my feed, I say, okay, for your user ID, give me the 20 most recent items sorted by post ID, and it's stored in memory or on disk, or however it does it internally, so they can read it straight off. So this means instead of jumping all over disks or tables or whatever, ultra fast in, let's call it a few milliseconds, I can get back an entire feed. So I do a lot of extra work on write. I write it to lots of people's inboxes so that because in Cassandra, writes are super cheap, right? Reads are fast, but there's no way to magically make reads super cheap. So because writes are super cheap, I can pre-organize all the data so that when a user logs in and reads, I can have their data there in basically no time, right? And the reason I'll talk about Kafka and Storm is how do we manage all these writes, because I don't want to do a ton of writes on a web thread. For those of you who are web developers, you know exactly what I'm talking about, right? And then I denormalized a bunch of the data. So when they do that load, they get all of the data they need. Basically, we can do one read that basically reads one range of things, not a really complex query, and you instantly have a feed-based app. It's, while SQL queries might make it look kind of easy, in terms of the actual work going on, this is in a lot of ways an order of magnitude easier. It's kind of pretty magical when you get down to it. So let me check how things are going time-wise. Good, I'm gonna tear through just a few quick notes about some of the other stuff we're doing, but time-wise, I think I'm pretty much getting close to my limit, so I'll just mention for queuing, in previous projects we used RabbitMQ, which is a very traditional queue. It's written in Erlang, it's great. It's apparently become a lot more stable. I've managed to make it tip over in a lot of cases and had all sorts of weird problems with it, but those are probably not a practical worry. But that's a queue in a traditional sense. So a lot of you have probably worked with queuing systems. They think of things like messages. You write something, someone's responsible for it at a certain point in time. You read it, you act the fact that you received it, then the queue can delete and say it was delivered to its intended recipient. Kafka is not actually a queue. It's a distributed log. So you think of a log being just a sequence of things. And Kafka, I'm going to kind of skip over some of the distributed aspects. But fundamentally, it lets you do replication, kind of like Cassandra, and it writes it as a sequence that can be read really fast. The interesting thing is, it has no notion of states of its client. So you can say, I'm going to write to it, keep the data around for 7 days, and clients can come and read it as they want. So what they do is, clients are responsible for keeping track of where they are. So they've said, they might keep in memory, I've read up to item 10. So then, a little later, they hit it, and they say, oh, are there new items? Yeah, well, there are items past 10. Read items 11, 12, 13, 14. So they can just read, and their clients are responsible for keeping track of where they are. So this makes it easy if you have all sorts of different reader services that are operating at different rates. They can all read from the log at their own rate and process items in a distributed manner. In practice, because we want to keep track in a distributed system of where the readers are, we use Zookeeper to keep track of that. But that's an important but tiny implementation detail. So I think I mentioned a lot of this. It's basically one of the lessons in a lot of this is sometimes dumber is better, right? If you make the core idea of something dumber, you can then start to put a lot more logic out on the edges. And that's a little true of Cassandra and a lot true of Kafka. This is details that you probably don't care about unless you're getting into it, having to do with how brokers write to disk at various points, and consumers read a range of stuff. Now, the last thing I'm going to mention, and probably, unless you feel like asking some questions, at the same level of detail as we talked about Kafka, which is to say, I'm going to tear through it pretty quickly, is Storm. Storm is a really cool system that we're having a lot of fun playing with. And Storm is, to start out, think of it a little like real-time persistent Hadoop, okay? So how many of you, I assume this is a big data group, so I'm going to see a lot of hands, but how many of you have used Hadoop? So a pretty good percentage, most of the folks here. And the way you think about the universe is we've got steps, right? And you've got map step, reduce step, sort step, map, reduce, sort, and you run things through these steps, and each step streams data and processes it. So you're streaming lots of tuples of data. So each item you process and move on and do the next thing. Storm is kind of like that, but you have persistent processes. So you have processes that are always just sitting there running, and then tuples start coming in a stream, and you process them. So we have tuples, and then they are in streams. They're emitted by what we call a spout. So you've got something that's emitting them. In our case, we built a Kafka spout. So it just reads from Kafka and starts emitting tuples into Storm. And you have bolts, which are processes that transform a tuple. So they read a tuple, they process in some way, then they can emit 0, 1, 2, however many things. The magic is how you construct topologies, which are basically graphs in the computer science graph sense of these spouts and bolts. So you can say, okay, this particular bolt is connected to other bolts. It takes its tuple and it sends it to other bolts. And you can tell it to do it in lots of different ways. For example, you can do a shuffle grouping, which just says choose any random bolt, and in practice does some load balancing across them, but choose any random bolt and send it to them. Or it could be a field grouping, where based on some key, it actually sends it consistently to the same nodes, which lets you cache things locally on the node, accumulate things. So you can imagine, I guess the classic Hadoop example is word count, right? And you always say, okay, well, I'm going to map things and then emit each word and count them up as I go. Well, you could use a field grouping to say, hey, take, let's say we're doing a word count. Words that start with A through F go here, F through Q go here, and Q through Z go here. It's an awful balancing of the alphabet. But now each one could locally cache a little bit of the alphabet and start accumulating words. So this is emitting words, these are emitting counts as they go. So you can use these different types of grouping, like broadcasts, fields, that sort of thing, to build really interesting structures. So fundamentally, that's the core idea behind Storm. We do a lot of interesting stuff with it, but I feel like I wanted to give you guys some time to ask some questions or discuss some of what sorts of tools you're interested in.
Hi. Could you describe how you handle photos?
How we handle photos?
Yeah, with Cassandra.
Yeah, so we actually don't put them in Cassandra. Cassandra does have a blob type for them, but we, for reasons having nothing to do with Cassandra, don't put them inside of there. We upload them, because we're on Amazon, to S3 directly, and the reason is we didn't want our web servers handling all the bytes of those moving back and forth. And so we generate a signed URL with a one-time permission to upload to S3. Then it does a web callback on the client saying, hey, it's done. The server then, there's a whole separate set of image processing servers, and they do all the transforms they need. So. I can't see who said that, but apparently we're doing something right. Absolutely.
Thanks. Could you talk more about your data center issues? I know you guys are just in like one region. If you could share more about the transfer between zones and Kafka movement, all that kind of stuff. So just more detail about your use of AWS and replication, etc.
Yeah. So what we do, and I'm primarily the developer. My friend Jeff is more the DevOps guy. So there may be slight inaccuracies in what I say here. So we operate in AWS today. Our plan in the long term is to be multi-vendor, in the sense that we want to be in AWS plus some third-party vendor. And what we did is we are planning to start out at 5 nodes. So we're going to run 2, eventually hopefully we get so big that we want tons of nodes. But what we're doing is we have 2 data centers that are actually live data centers. So in Amazon world, US West 2 and US East 1. And what we do is in each of those, we have 2 Cassandra nodes. Then we wanted a tiebreaker in case one of the data centers, in case there's a split brain, we wanted a tiebreaker. So in US West 2, San Francisco, which is most likely to have an earthquake, or sorry, US West 1. US West 1 is San Francisco, US West 2 is Portland for anyone who cares about Amazon Web Services world. So in the place that's likely to have an earthquake, we just have one AWS node one Cassandra node that exists as a tiebreaker, but currently we don't have the rest of our services running there because we're planning to be 2 data centers to start. So the reason why we said we want to be multi-data center from day one, being a small app, being multi-data center is sometimes a little overkill. Cassandra is actually really good about, you just want to add a data center, that you can do in seconds. Zookeeper is a huge pain in the ass to reconfigure. If anyone's dealt with Zookeeper, adding nodes to Zookeeper, it just doesn't like it. So it's easier to pre-build out your cluster knowing exactly what the IPs of every Zookeeper will be. So our idea was, hey, let's start with 3 data centers so that we don't have to deal with Zookeeper having problems doing it at some point in the future. And we said, so then to get into some details, each data center has the whole host of services outside of, at least these 2 main data centers of US West 2 and US East 1. And each data center then has an ELB, varnishes, UWSGs, and a bunch of Cassandra nodes. Then each one has also a chat server, a Kafka, and a Storm. Okay, so those exist a copy on each data center. Then within Amazon, you have to explicitly open ports for services to talk to each other. So you create tunnels for individual services to talk. The only services that talk that are actually aware that other data centers exist, our chat server has some internal communication, but ignore that for a second. Fundamentally, the services that are allowed to talk between data centers are Zookeeper and Cassandra. So everything else is pure data center local. So if you think of a Kafka server, it gets stuff off the chat server or the web server, it's queued in Kafka, it goes to Storm, but that's all processed locally, and ultimately the end results are written to Cassandra, and then that's how it ends up replicating into other data centers. So it's the previous things we built have had all sorts of cross data center chatter, and we said one of our goals was to get rid of complexity, to have very few points that have any kind of open ports between data centers. Anything else? Anything?
Nice presentation on architecture there.
Thank you.
I have a question about, tell us about your data modeling experience. How do you use Cassandra collections, maps?
Yeah, so...
What is the typical example you would like to store there?
Okay, so you're talking like the sets list maps, those collections. So we don't use them that heavily. And in part, that's because when I first learned it, that you could have done it with super columns and stuff, but they didn't really have it. So that's actually a pretty new feature. So I'll admit that I'm not a super expert at it. We use sets a lot. For example, sets of permissions. We also keep track in those. So if I go back here to this post table, I think we... Okay, so here you saw we had the post in the inbox, right? And you'll notice that the post had an ID. It actually does keep a set of recipients, okay? And that's all the people whose inboxes it went to. And the idea there is, because we're not using their secondary indexes, because we're maintaining it ourselves, if someone then decides they want to delete a post, what we do is we have the post ID, so we can load the post ID, then we get the recipients, which is a set in memory, and then we can just go to each corresponding inbox item where we iterate over for each recipient, get that post ID in their inbox. To do that because I'm not in present mode. Then we can iterate and delete each corresponding inbox item. So that's an example of how we use collections. I'm sure there are a lot of fancier use cases. We just don't happen to do many of them, but it seems like there'll be a lot of them. Anything else I can answer?
Just with your usage of Storm, could you maybe give us an idea of how you tie that into like the application interface? Because I know Tappy talked about it as logging, but with Storm, I mean, like for example, like Twitter, they use it to process every link, so you can kind of tie the use of the technology into something in the app front end. Could you maybe give us a picture of what you're doing?
Absolutely. So what happens is, and we had planned to do some much more complex use cases that ended up getting cut as features from the app. So arguably for what we're doing today, Storm is massive overkill, but we have built a lot of our infrastructure in terms of it. We do distribution of posts. So let's say you send a post to 100 people. What happens is you send it, it goes to the web server, and we write the post immediately from the web process to Cassandra. Then we want to distribute it to 100 people. In practice, Cassandra is so fast that you can do it in the web process. We were planning to do some much more complex use cases that would be an order of magnitude more complex, so we do the writes async. And I think it's just good practice not to do multiple, not to do multiple writes off a web server. You should always be doing them on some backend queue. So what we do is we put them into Kafka. Then as we're reading them, we load each one, we say, who are the recipients? Then we put them into each user's inbox. But then we also, for each one, evaluate a bunch of rules. For example, we have rules about when do we send a push notification. We don't want to annoy people, so if you get 5 messages in a minute, we're not going to send you 5 Apple push notifications. But the Storm server is maintaining connections to Apple's push notification server. So there's a bolt in there that says, so for example, the spout gets a post. Then there's a bolt in there that says split this one tuple into tuples for every recipient. So that will take the one post and split it into n tuples, which are each of the recipients. Then each of those we evaluate rules on. So it goes to, oh, here's a recipient. It will go to the appropriate bolt that says evaluate the rules for that recipient, which is, one of the rules is figure out if they're supposed to receive a push notification. So that node keeps a little cache, or it can load it from Cassandra if it's not cache, of here are the recent things I've seen for that user. And based on some stuff, it'll decide, no, I'm not going to send them a push notification, or I am. So then it'll write it to Cassandra, and if it is supposed to send a push, it has another bolt that will then format it and get the correct messages and send it out to Apple's push notification. So very simple set of steps in our case. One of the things that you mentioned was Twitter's case, which is in some sense a far more interesting use case for it, where Twitter uses it to figure out what the reach of an ad is, right? So in Twitter's case, they do advertising where you buy a promoted tweet, and it will basically, anyone who reads your friends' things will see it. So what happens is, it goes out across their graph, but most people, because of the structure of social networks, I may have the exact same friends as you, right? Or a lot of them. So if I have 100 friends and you have 1,000 friends, right? The number of people who then read that ad isn't 1,100, right? It's probably like 1,005, right? Or some subset, because most of my friends are also your friends. So they do a lot of the deduping and figuring out how the graphs go by doing that in Storm. So they do each step as a bolt in Storm.
Thanks.
Absolutely. Any other questions?
Just curious, why did the consistency factor of 1 work so well?
Yeah.
Is that if you make that right, and then somebody asks for the result, maybe they'll get the wrong result, but it's kind of usually doesn't happen that way.
Yeah.
So small.
Well, there are a few different things going on. So first of which is, let's say you have something and you do an update, right? It turns out to be pretty fast. It's actually so fast that just the replication across nodes, usually you just don't notice the fact that it still hasn't replicated. We also do a lot of inserts. And I don't know all the internal mechanics, but what they do in Cassandra is if they don't find it, rather than saying not found, they first do this ask other nodes, does it exist? So they do the replication as part of the query. So if you're really only inserting, if it exists on one node, you'll get a result, even if it hasn't replicated to the node you happen to be asking. So that's why if you're doing a lot of insert-centric stuff, writing with one, you write, say over here, you ask over here, it then, through its gossip protocol, broadcasts. And don't quote me on the mechanics, because I'm not a Cassandra internals person, but it basically says, hey, at least within this time bound, can I find out where it is? it says, oh, it's there, it gets it, now the node has its replica, and it returned you a result. So by even writing it one and reading it one, I got my correct result, even though I wrote and then immediately read. Now, any wouldn't have that same property, because it wouldn't know where to look, which was the lower consistency level, that it was just write it somewhere, but not even the node that's supposed to own it. And that could have problems. But one seems to be, I thought everything should be quorum, and the one thing I've learned is, hey, for really important data, make sure you're at least writing in quorum. If you care about making sure it's consistent in a use case, you can do that by writing in quorum and reading in quorum. But for just very simple cases, you can write it one and read it one. So, perfect. Thank you all so much, and I'll stick around for a few minutes if you have other questions. Yeah, really excited. If any of you want, also, we haven't launched our app yet, but if you go to trytappy.com, you can at least put your name on it, and I'll send you an email when we have a beta, or just grab me and I'll grab it. But thanks so much.
Just want to remind you guys, we have another meetup next Wednesday. It's going to be on Spark. So it'll be great for you guys to come down for that. Thanks again for coming.
When's the Spark one?
Next Wednesday.
Next month?
Next Wednesday.
Next month? Oh.
Thank you.
Yeah, you know, I'm on the business side, like,